I now call to order the lecture portion of the Society's 2518th meeting and the 94th Joseph Henry Lecture in what is now the 154th year since PSW was founded on March 13th, 1871. Good evening, everyone. My name is Larry Milstein, as some of us seem to know. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. And welcome to our members, guests, and friends to the lecture part of today's PSW meeting and to the lecture by Jason Dworkin on OSIRIS-Rex and the analysis of the samples it brought back from the asteroid Bennu. First, let's thank our sponsors. PSW is very grateful to them. And let's start by thanking Mike Helton and Helton Associates, LLC, who have been the generous sponsors of the whole year's lecture series. Mike is staying clandestine in the audience somewhere, but we are very grateful to you, Mike. Thank you so much. And also to series sponsor, PSW member Joe Shulman, who isn't here, but thank you, Joe. And finally, to the sponsors of tonight's lecture, which would be Robin Taylor, who's in the back there, and somebody named Larry Milstein. The Society needs your support to meet its expenses for the year. So if you're not given or feel you can give more than you have, please don't hesitate to donate. You can do so via the webpage, or we'll be glad to accept your donation as long as it's not cash. Oops, all right. Tonight is the 94th annual Joseph Henry Lecture honoring PSW's founder, first and longest serving president, Joseph Henry. Henry served as president of the Society from its founding in 1871 until his untimely death 7 years later in 1878. He was the preeminent American physicist of his time, an American Maxwell, and also perhaps the most prominent American scientist of that time. He's best known for his many contributions on electricity and magnetism, and for his finding that a powerful magnetic field is induced by flowing current through an insulator conductor wound around a ferrite core. His work leading to the development of very much stronger electromagnets. His work on induction and inductance led directly to the invention of the telegraph and later to the invention of the telephone. In fact, Henry developed early versions of the telegraph and consulted with Samuel B. Morse, who ultimately supposedly invented the telegraph system that came to be widely adopted. Among his roles in founding and serving in many other institutions to foster science in America, Henry was also the founding secretary of the Smithsonian Institution. His death was headline news not only in America but also around the world. And here in Washington, D.C., the city quite literally closed down to mourn his passing. We honor Henry today with this annual series of lectures on important topics in science that would certainly have interested him. We also honor Henry today by using the Society's ceremonial gavel, which was carved from timbers of the White House recovered during the Truman Reconstruction of 1949 to 1952. The timber used to make this gavel originally was used in the White House reconstruction of 1815 to 1817 after the bridges, those of the famously special relationship, burned it to the ground. And I like to say that just goes to show enemies can become friends. I am pleased to announce the following new members: Michael Ryan, a physical volcanologist with the Magma Physics Project, interested in rheology and flow mechanics of magma and silica melts in volcanic interiors and in the internal structure of active volcanoes. Michael has known about PSW for quite some time at least since he gave the PSW meeting lecture on November 30th, 2007 at the 2229th meeting. Back then, speakers only received 1 year of dues-free membership, so he has to rejoin. Speakers now receive free membership in perpetuity. But we welcome if they want to pay dues. James Towns, a telecom consultant, broadly interested in science and in ham radio, who is a longtime Zoom and YouTube viewer of PSW lectures. And tonight's speaker, Jason Dworkin, who learned of PSW from our invitation to him to speak here tonight and whose interest will be clear in part from his lecture. So please join me in welcoming them to membership. If you're not a member, why not? Please join. It's easy enough. You only require a genuine interest in science and a willingness to pay the annual dues, which have not changed in 20 years. So it's a bargain, half what it was originally. You can do so by accessing the homepage on the website. At the upper right-hand corner, there is a blue join button. You click on that, and I think everybody here knows how to use the web. You follow the instructions, fill out the form, pay some dues, and your membership application will be reviewed and most likely will be accepted. So please do join. You can also access information about PSW and access the membership application form using the QR code on the back of the business cards that are on the cocktail tables at the back of the room. And we try to ply you with cocktails. No, we don't. All members are entitled to receive a wear the ribbon, and also are entitled to receive a free copy of the PSW Bulletin, Volume 17, published last year, which contains many of the seminal papers and several histories of PSW, a list of Joseph Henry speakers and other interesting facts about the society, signed by me on behalf of the membership. You also get to come to dinner with the speaker, and here's just a few pictures of the fun times that we have, like tonight. You may recognize some of the faces in here who are also in the room tonight. And this is a cake that we made in the shape of the Smithsonian Castle where PSW was founded. So please join. We welcome new members. Recording Secretary Scott Matthews will now present the minutes of the 2517th meeting and the lecture by Alex Creeley on commercial energy from fusion. Scott, the stage is yours.
Thank you, Larry. On June 13th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2517th meeting of the Society to order at 8:05 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Mark Palmer, titled The Path to an Energy Frontier Muon Collider. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Alex Creeley of Commonwealth Fusion Systems. His lecture was titled Commercial Fusion Power, High-Temperature Superconducting Magnets and Compact Tokamak Power Plants. The speaker began by saying that fusion potentially provides power that is clean, firm, safe, scalable, and secure. He discussed the process of fusion, taking small atoms and combining them into larger atoms while liberating large amounts of energy. He described DT fusion, the most common type of hydrogen fusion. He described the nature of plasma, indicating that temperatures on the order of 100 million Kelvin are required for fusion, and that all matter exists as plasma in this temperature regime. Creeley then introduced the tokamak, a toroidal-shaped plasma reactor which relies on magnetic confinement. He described how the Lorentz force causes charged particles to orbit around the magnetic field lines, thereby confining the plasma. He claimed that more than 100 tokamaks have been built, and that while many technical questions remain, much of the physics has been worked out. He described the geometry of the magnets in a tokamak, including the central solenoid, the toroidal field coils, and the poloidal field coils. The speaker then discussed the company Commonwealth Fusion Systems, or CFS. Founded in 2018, spun out of MIT, raised more than $2 billion in venture capital, a current workforce of more than 1,000 employees. He described the company's mission as taking the relatively well-understood physics of tokamaks combined with a fundamentally new magnet technology to create a commercial demonstration called Spark. The lessons learned and the technologies developed from Spark would allow them to build a commercial power plant called ARC. He said that ARC would be a commercially available product operating on the grid. He mentioned that CFS publishes papers in peer-reviewed journals regularly and that the company supports the open dissemination of information on plasma physics. Creeley mentioned the collaborations between CFS and more than 100 laboratories around the world. The speaker then discussed magnet technology. He described how increasing the magnetic field can increase the confinement time of the plasma and also decrease the overall size of the tokamak. He said that in 2021, CFS, in collaboration with MIT, developed a new type of high-temperature superconducting magnet which produces more than 12 Tesla at its center, approximately twice the field of the previous generation of tokamak magnets. He said that these new magnets are now in commercial production. Creeley described the Spark demonstration plant, designed on the same physics as ITER, but at a reduced size, currently under construction just outside Boston, initially planned to be operated at Q greater than 1, but able to achieve Q equal 11, producing 140 megawatts of fusion power. Its primary goal is to, quote, learn for ARC. He discussed how Spark will be used to investigate heat exhaust solutions to be implemented on ARC. ARC will be a commercial fusion power plant considerably smaller than ITER, producing 400 megawatts of net electric power, planned to be built in Virginia in the early 2030s. Creeley said that CFS intends to deploy thousands of ARCs around the world by 2050. The speaker discussed getting energy in and out. The energy in, to heat the plasma, is provided by radio frequency waves. The plasma-facing components are made from or coated with tungsten. The fusion-generated heat comes out through the diverter and also via neutrons. The neutrons will be absorbed in a molten salt blanket made from the material phlebe, a mixture of lithium fluoride and beryllium fluoride. The phlebe serves three functions. It absorbs neutrons, it acts as a working fluid for the primary heat exchanger, and it breeds tritium, one of the hydrogen isotopes required for fuel. The speaker ended his talk by saying, quote, fusion is the basic process that powers the universe, and it is potentially a huge game changer in the energy industry, end quote. The lecture was followed by a question and answer period. A guest asked if the U.S. was the most likely place for commercial fusion to be developed and if the regulatory conditions played a significant role. Creeley responded that CFS chose the U.S. as the site for their first commercial plant, partly because of the regulatory requirements were well defined. He said the majority of private companies pursuing commercial fusion are in the United States, largely because the U.S. offers a good talent base and a venture capital system for these types of efforts. A member asked for specifics on the high-temperature superconductors used to fabricate the magnets. Creeley said that the material is yttrium barium copper oxide, or YBCO, in a thin film deposited on a metal ribbon so that it remains flexible. He said that CFS purchases these ribbons from commercial suppliers. A member on the live stream asked what the projected lifetime of the plasma-facing components would be, given that the high-energy neutrons are not kind to most materials. Creeley responded that the entire plant would have a lifetime of about 20 years, but that the vacuum vessel closest to the plasma would be replaced every 1 to 2 years. President Milstein then asked how the radio frequency waves were generated and coupled into the plasma. Creeley said that solid-state power electronics are used to generate the RF, which is coupled into the reactor using a high-power coax waveguide. Inside the reactor, antenna structures launch the RF into the plasma to generate heat. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2,517th meeting of the Society at 9:54 p.m. Eastern Time. Temperature in Washington, D.C., 25 degrees Celsius. Weather, mostly cloudy. Attendance in the Powell Auditorium, 54. Viewers on the live stream, 43, for a total of 97 viewers. Views of the video in the first 2 weeks, 778. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott, for superb minutes. Once again, are there any comments or corrections or additions to the minutes? I have one small quibble. I think the magnet technology was developed only at MIT, and then Commonwealth came in and used it. I don't think that Commonwealth actually developed it, although they might have had a role in learning to manufacture it in a large scale. Other than that, I will accept a motion to accept the minutes. Second, all members in favor? All members opposed? Minutes are accepted, subject to that one provision, and will be posted to the website in due course. For those of you watching online, if you have any issues, you can communicate them to corresponding sec@pswscience.org, and they will be duly considered. And we now turn to tonight's lecture by Jason Dworkin. Jason is the project scientist for the OSIRIS-Rex asteroid sample return mission and senior scientist for astrobiology at NASA Goddard Space Flight Center, where he also directs research at the Goddard Astrobiology Analytical Laboratory. His research is on organic species available for the early evolution of life and its origin, focusing on well-documented and constrained systems, including plausible early Earth chemistries, the chemistry of astrophysically relevant laboratory ices, the organic and chiral analysis of meteorites, and the analysis of samples returned from extraterrestrial bodies. And he's directed considerable effort developing ways to protect extraterrestrial samples from contamination. He's worked on samples returned to Earth by the NASA Apollo missions, JAXA's Hayabusa and Hayabusa 2 missions, and by NASA's Stardust and OSIRIS-Rex missions. And he is now a participating scientist on JAXA's MMX mission to return samples from Mars's moon Phobos, which, incidentally, was discovered by PSW member Asip Hall. Jason also serves as sample integrity scientist for the Mars Sample Return mission, whose fate currently, unfortunately, is uncertain. He's an author on over 190 peer-reviewed publications related to astrobiology. Among other honors and awards, he's a recipient of a NASA Outstanding Leadership Medal, numerous NASA Team Awards, including 2 Silver Achievement Medals, the Maryland Chemist of the Year Award, the Goddard Center Directors Award, 2 Guinness World Records, and most recently the Michael Collins National Air and Space Museum Trophy for Current Achievement. And to top it all off, asteroid 27347 Dworkin is named in his honor. Jason earned an AB in biochemistry at Occidental College and a PhD in biochemistry at UC San Diego, where he walked in my footsteps. It's a fantastic little school on Torrey Pines Mesa overlooking the Pacific, and I recommend it to any student seriously interested in studying science. And I'll be happy to talk to anybody who is. All questions will be fielded after the lecture during the Q&A session. With that, Jason, the stage is yours.
Thank you very much. Thank you. Wonderful. Thank you for having me. It's a pleasure to be here, and especially in honoring Joseph Henry tonight. So this is the OSIRIS-Rex mission you've heard a little bit about. It is, here's the asteroid that I'll be discussing. It is a half-kilometer across asteroid that the spacecraft went to and collected a sample from. This is currently on board the spacecraft. This is a plaque in honor of our first principal investigator who sadly passed away a few months after mission selection in 2011. And so we dedicate our work to him going forward. Space. This is a beautiful image of the Orion Nebula taken by the James Webb Space Telescope. One of the great things about this image is you can see the formation of another solar system here. So for scale, this is the orbit of Neptune, so it's a very large object. And this is represents the infall of material, the mixing of material from space into this solar system that's forming. Much has happened over 4.5 billion years ago in our solar system. At some point, so roughly 4.4 billion years ago, the Earth was bombarded by objects from space, which may have helped spark the origin of life. We don't know much about this period of time. The geologic records are lost by geology, but this is one of our main pursuits. And to understand how we, right here, fit in all of biology, which is represented by this rRNA tree. And you can see that our close neighbors are, well, no offense, but a rat right here. And then just next to it is corn and fungus. And we're all very, very closely related with the same sorts of chemistry, the same biochemical mechanisms that are found throughout life on Earth. We're all part of the same history. And so this is a cartoon from XKCD. If you don't read it, you probably should. That says that asks the question about the early Earth. What was it like here 4.5 billion years ago? All we have are a little bit of crust left over, the material that hasn't been lost to subduction by the formation of continents and the movement of geographic stratigraphy to form the material that we see today. So unfortunately, Earth is quite quiet on that. All we have are these super tantalizing zircons and scars on the face of the moon. The zircons tell us that some 4.4 billion years ago there was an ocean on the Earth, and the scars on the face of the moon tells us that there was a bombardment history, that the Earth was not disconnected from the rest of the solar system, the material was infalling. But again, this material was lost to the hills. And so I love this quote from Neil Armstrong that geologists have a saying, rocks remember. So why do we look at rocks? Because they remember the past. And that's what we're interested in. So there's a number of processes that happen. I alluded to some, the formation of dense clouds that then form stars and planets that you saw in the Orion Nebula that eventually lead to stellar death and depositing material in the diffuse medium, then back to the dense clouds. We understand these areas by doing remote observation and simulations. These materials can then fall onto primitive objects like the early Earth or Mars, Enceladus, Europa, Ceres, where have you. And we understand these by looking at simulations of these objects in the laboratory or in models. But these materials in between, these are the messengers we can look at directly. Now, infrared spectroscopy and spectroscopy in general is great. You can look at things a distance away. You can look at, for example, the difference between a gas and a solid. Here's an ice and gas made of the same material. They have definitely distinct species. The same elements recombined into methanol instead of as the individual water and carbon dioxide. Quite distinct. When it comes to complicated species, you can't really tell the difference between an apple and an orange. But get it into the laboratory, You can separate these materials out physically in space on using chromatographic techniques. And you can tell the difference between an apple and an orange and say that, well, gee, apple juice has more fructose than orange juice, for example. Something you cannot do with a telescope. No matter how good it is, you won't have the resolution to see this level of detail in the samples. And this is where the chemistry lies. It tells us about the origin of life in the great detail that we need to say something about the molecules beyond the overall levels that you get from spectroscopy. So the way we access these is by looking at materials we can get into our laboratories. That's meteorites, interplanetary dust particles, and sample return missions from asteroids and comets. These are our witnesses. And so there's a lot of asteroids I'll be talking about. Here's a model of the main asteroid belt. So Mars, Jupiter. Here's the Lucy mission headed towards the Trojan asteroids, and the Dawn mission that went to Ceres and Vesta, and the Psyche mission headed to asteroid Psyche in the main belt. And what we can notice here is that there's a lot of different structures within the main asteroid belt, including a lot of different kinds of chemistry indicated by these colored lines. And so asteroids which are have the spectra consistent with organic compounds, like C-class and B-class, have been visited by spacecraft I'll be discussing. And one of them is Ryugu, which was visited by the JAXA Hayabusa 2 mission, and the other one was Bennu, visited by the OSIRIS-Rex mission, and also Itokawa, which is the stony asteroid of depleted in volatiles, visited by the first Hayabusa mission. And so we can look to Joseph Henry's statement about looking at the late Mr. Smithson's sample of rocks in a cabinet, and some of them had some important meteorites, which have fallen in Europe over the centuries. One of them is, for example, this one. This is the first meteorite, the thunderstone that was observed to fall in the Pyrenees in France in the 1400s. But there are also some other examples, and this one is an ordinary chondrite, fairly common. Here is an iron meteorite that you may have seen in museums. They're beautiful to look at, and they represent a small fraction of the falls, but a large fraction of the finds because they're so they're big, heavy irons. They don't rust away very easily. Pallasites are gorgeous. They're basically peridots trapped in a matrix of iron and nickel. And then there are these ugly ones. This is the Orgueil meteorite, which also landed in France in the 1860s. I've now forgotten. These are the carbonaceous chondrites. So these are the types of meteorites that contain primitive organic compounds, are rich in water, rich in volatiles, the stuff that maybe went into making life on Earth or elsewhere. And so it's also fortuitous. I'm speaking today. Monday is the International Asteroid Day, which is the anniversary of the Tunguska impact, which was a dinky little 50-meter diameter stony asteroid that exploded over Tunguska, Russia in 1908 with about a 12 megaton explosion. So for comparison, this is the blast area versus the size of Washington, D.C. It's a very remote part of Russia, very hard to get to, and so only many decades later were there photographs taken of all the trees knocked down. It's a nuclear level type of explosion. So although asteroids can give us lots of great information about the origin of the solar system, origin of planets, they're the leftovers of planetary formation. They also pose a potential hazard that we should respect and try and understand. So there are a lot of places to look for extraterrestrial samples. One can go and look at folks who do it for fame and profit, and they get their meteorite samples from places that have to be kept secret because poachers can go in and steal their finds. But that's really bad for science because we don't know where they are, and they are held with his filthy little hands. There are other meteorites. So, for example, this is the Alma-Hatsasita meteorite, which was formerly known as asteroid 2008 TC3. That's the first case of an asteroid that was observed and then became a meteorite. It landed in Sudan just a few hours after it was detected. And here, a group of students and scientists are pointing at the samples that they found and picking them up with tongs and gloves. Thank you very much. There's also an annual trip to Antarctica. There's a Japanese trip, but there's also a U.S. trip by the NSF and NASA, which goes and collects thousands of meteorites. Antarctica is a great place to get meteorites. They land all over the Earth all the time, everywhere. But meteorites tend to be black. Antarctica tends to be white, so they're easier to find. Plus, there's some nice geographic features that allow the glaciers to move in a direction to concentrate meteorites up, so that there are areas with higher concentrations than other places on the Earth. And so, in this case, you can't see him right here. This is the PI, principal investigator of the OSIRIS-Rex mission, in the background, as well as my colleagues and Danny Glavin, who I work in the lab extensively with, and we hear some of him as well. And so in this case, we don't know much about the sample. Here we collected dirt from the place that it landed, but it is full of dirt. Here we collected some ice from the area, so we can look at that as a background, because meteorites always land in the ground. And Antarctic ice is really, really clean. But ideally, you go to the source. And so to steal from the untouchables, if you're afraid of getting a rotten apple, don't go to the barrel, get it off the tree. So going to an asteroid itself, we know where that sample came from. We have an impeccable chain of evidence about how it got into our laboratories. And so we, with the exception of this one and a couple others, we don't know where these meteorites came from. Did they come from a comet or from an asteroid? What kind of asteroid? Here we know exactly where on which asteroid the sample came from. So we have a lot of provenance of the sample. It gives us a lot of information context. And so sample return missions are the gift that keeps on giving. The very first sample return mission was Apollo 11, which brought back samples in 1969, obviously. It was also fortuitous that two of the largest carbonaceous chondrite falls that happened were in 1969, one in the fall and one before in the spring, which served as great examples for scientists to practice on before they got these samples from the moon. Turns out the lunar rocks are really poor in organics. They didn't know that at the time. There were hot debates over whether or not the lunar material was black because of organics or because of basalt. My academic great-grandfather swore up and down that it was organics. He was wrong. Well, he only got one Nobel Prize, so that's fine. But anyway, so there's a history of sample return missions from the moon in both robotic and astronaut-led missions, including at some point Artemis 3 and 4, and who knows beyond that. Then there was a long pause from the last sample return mission, 1976, to the next one, 2004, for the return of the Genesis sample that collected solar wind, particles and atoms from the sun. Then the Stardust mission returned samples from a comet Wilt 2, that we were able to analyze in the laboratory and actually find the first amino acid detected from a comet. I've already mentioned briefly the Hayabusa mission and then Hayabusa 2 and OSIRIS-Rex. They went to the comet, they went to asteroids and returned samples from either a stony asteroid or a carbonaceous asteroid, carbonaceous being rich in organics by comparison. You heard about briefly the JAXA mission to Phobos, and we don't know the status of Mars sample return, so we'll see what that's like in the coming years. So the OSIRIS-Rex mission, the main thing I'm here to talk about, the OSIRIS-Rex is a long, tortured acronym that describes the mission priorities. For me and for most, the top priority is origins. Return and analyze a sample of pristine carbonaceous asteroid regolith. We also are interested in the spectral interpretation, that is to understand the ground truth for what telescopes observe. We cannot send a spacecraft to every single asteroid, but we have spectra of lots and lots of asteroids, so we can compare them with what we see in the laboratories. Resource identification, That is to map the asteroid, and in this case, we also learned how to fly around an asteroid, which is in this case an object that's very small with minimal gravity. So in the future, when there are folks prospecting for mineral riches in asteroids, maybe for their own fusion reactors or what have you, we know how to do some of that now based on this mission. Next is security, to understand what's called the Arcosty effect. I won't have time to go into much, but this is the unexpected movement of asteroids based on the rotation and dark color and absorbance of light that can shift their trajectories away from what's expected, which is why making long-term predictions about the location impact hazard of asteroids is complicated and difficult. So we've been able to refine this. And finally, Regolith Explorer, to document the asteroid down to the sub-centimeter at the sampling moment. So there are a lot of asteroids. When we designed the mission, I'll tell you first that, so here is Sun, Mercury, Venus, Earth, Mars. Here's the orbit of Bennu, which is our target asteroid. It crosses Earth's orbit, but does not cross Mars's orbit. Here is Jupiter, and there are the Trojan asteroids going by, the target of the Lucy mission. The green asteroids are the main belt that I alluded to before. Yellow across Mars, and Earth crossing asteroids are in red. So when we first designed the mission, there were only 500,000 asteroids known. There are now over 1.3 million. But it takes a long time to propose a mission and develop the concept. So how do you pick the one asteroid you want to go to? Well, it was very important to us to have the science and engineering team survive the duration of the mission. And so that meant we needed to go to a near-Earth asteroid. Going to the main belt and coming back would just take too long. Plus, that would really extend the patience and budget of our benefactors. So we needed, so that brings us to one of these near-Earth asteroids, one of the ones in red. Of those, we needed an asteroid that had a good orbit, so we could use a rocket that existed and we could afford. So the inclination of Bennu, the orbital plane change of Bennu versus the orbit of the Earth, is only inclined by 7 degrees. So that means that there's less energy to get there. It's much easier, so we can manage that. Of those, we needed an asteroid that had a diameter of at least 200 meters. And that's because there's, related to the Arcosty effect, there's something called the Yorp effect, which is where the photons impacting the asteroid, if it's very dark, can apply a torque, and the asteroid can spin up faster and faster and faster, up to 1 revolution per minute. And that poses 2 problems. One is we want our navigators to be able to precision navigate the spacecraft to touch, collect a sample from the asteroid. And at that kind of speed, the navigators would have an untimely heart attack and death. So we cannot let them suffer that fate. And secondly, our sampling device is designed to pick up loose rocks and regolith. And if it's spinning that fast, all that regolith is lost. Next, we needed an asteroid that was carbon-rich. We had information from ground and space-based observatories that told us that this was one of 5 carbon-rich asteroids that met all these criteria. Now, there may be many others, but not every asteroid that's on here has a spectrum. It's much easier to track the location of an object than it is to figure out what it's made out of. So, but we had a rich array of data that told us a lot about this asteroid. So we had a shape model from the sadly departed Arecibo Observatory, as well as Goldstone, that gave us a model of the asteroid, a shape of it. We knew its size. Here it is relative on the same scale to the Capitol building. So it is a fairly small object, but still big enough, 500 meters across. And we were able to buy down a lot of risk by understanding this object. We knew that it had thermal inertia, which suggested that it was full of loose pebbles of a sort of centimeter scale. We had the shape, so we could design the spacecraft to operate around that. We had the gravity. We had the time of day, 4.3 hours per day in rotation. We knew its rotational speed, its position, lots of information, so that we could design a bespoke spacecraft and custom mission to go there and get the sample. So here's our bespoke spacecraft. In many ways, it's like any other spacecraft you've seen. It has an instrument deck with cameras, etc. It has solar arrays. These are gimbaled so that you can move them around, which is great because Bennu is very small. And so that the force of gravity on that Bennu exerts on the spacecraft is on the same order of magnitude as the solar pressure from the sun. So it's important to maintain the same center of mass and center of area of the spacecraft. And so by being able to articulate the solar rays, you have that flexibility. The other weird thing is we've got this thing right here. This is a 3-meter long pogo stick. And here are all of the instruments. I won't go into much. But here's the end of the 3-meter long pogo stick is a what we call the tag SAM. This is a device that looks something like an old car air filter, and it's designed to pump in a blast of nitrogen gas to mix up the regolith and get it trapped in this trap, this old car air filter. The initial name for it, when in the design phase, was MooCav, which is vacuum spelled backwards, because that's basically how it works. It was designed by a Lockheed Martin engineer with a solo cup and air compressor on his driveway. It worked beautifully. The other weird thing we have is this thing right here. This is the sample return capsule. So after we collect the sample, we put this thing in that thing, cut off the pogo stick, and close it up and return to Earth. Easy peasy. So when you design a mission, NASA doesn't just give you a dump truck full of money and say, go do it. We spent a lot of time in reviews and designs. I've actually been working on OSIRIS-Rex or precursor missions for 21 years. The first mission was high risk and not a good design. We learned a lot. Our second attempt was much better, but was not selected. Instead, the Grail mission was selected, and that was a good decision because if this spacecraft we designed had gone to Bennu, it would have been a disaster. But we designed a bigger mission under a larger cost cap in the New Frontiers line, about double the cost of the Discovery line. Wrote a proposal that had to be driven to Alexandria to be submitted in 2 trucks. This was back in the old days, so we had to have 90 paper copies in 2 volumes. It wouldn't fit in 1 truck. Anyway, so we had lots of reviews and finally launch September 8th, 2016, which was on time and under budget. When I say on time, we did launch 150 milliseconds into the opening of the launch window, but I'll still count that as on time. So on the way, we had problems. Some unexpected things I'll be talking about. This is a 4-alarm fire in Hollywood, California. Inside this burning building was both the prime and spare optics box for the infrared spectrometer that was built at Goddard. Now, they weren't supposed to be there at the same time. It was a shipping error that caused them to be at the same building at the same time when they the plating shop was so happy with the work that they put the optics box on a table that they'd plated and the other one next to it so they could take some pictures and be really excited about how good a job they did. Well, that weekend the building burned down, and this is the optics box that you just saw here. It melted. This is molten aluminum. So this was bad, and that both the prime and backup were combusted. However, amazingly, the OSIRIS team managed to, had previously in 2013 when there was a government shutdown, had decided to, after that was over, they were allowed to go back to work. They didn't take the schedule hit. They worked extra hard to make up that lost schedule. And so that when this disaster happened, they had enough time and budget to be able to refurbish the engineering design unit, and that's what's actually flying on the spacecraft right now. So they were able to deliver on time and on budget, even though the prime and backup optics box melted. And if you're ever at Goddard in Building 34, you can go and you can look at this. It's on display. Here's another little thing that happened. This was an exciting day. This was we were getting ready to launch, and here is the OSIRIS-Rex spacecraft. It's on its fully fueled, sitting on its launch vehicle with a solid rocket booster. And then 1 mile away is the Amos 6 SpaceX static fire anomaly that exploded, created a huge plume of smoke that went over our spacecraft. When it exploded, there was a shower of rocket fuel, RP-1, that went and actually covered some of our technicians and their cars. Everyone was fine, but it was a scary time, especially because right between it, right here, you can barely see, there's a shared water cooling facility. And that was responsible for cooling both buildings down, this launch complex and that launch complex. The explosion knocked it out, and so we lost cooling water. And this being Florida in the early September, we were very, very close to having our flight batteries explode from the heat. But they were able to bring in tanker trucks full of cold water and were able to bring the temperature down and were able to launch on time. So here is the rocket not covered in smoke because it had been rolled out on the pad. Here's our team, our principal investigators, Professor Dante Loretta. I already mentioned Mike Drake, who sadly passed away. I was off doing an interview somewhere, so they put my picture on a thing. So I'm the project scientist down over here. And what does a project scientist do on a PI-led mission? Well, as I said, OSIRIS-Rex is a principal investigator-led mission. So Professor Loretta is the overall in charge of the entire mission. My role is to be the voice of science to the engineers, to be the voice of engineering to the scientists, and be the confidant and loyal opposition to the PI and project manager. In other words, I tell the scientists, I tell the engineers that what they're going to do is going to destroy the science. And then I tell the scientists that what they want to do is going to destroy the spacecraft. And I tell the managers that what they're going to do is going to destroy the team. So I'm everyone's best friend. But what that really means is I get to be the dumbest person in the room because I'm always I'm a scientist sitting with managers and engineers and accountants in every aspect of the mission, which is great. And I always get to ask, like, why do you do it that way? And usually they say, oh, because of this and this and this. But occasionally they say, why do we do it that way? Huh. And then we come up with a solution. I'm also, in addition to being project scientist, I'm in charge of the contamination science. And so I can butt my head in whenever it comes up and make sure that we're using materials and processes that keep the sample pristine, because that's all about getting the sample back. And so we had a design for flight from launch in 2016, long cruise to the asteroid with an Earth gravity assist to get in the right plane of orbit. Approaching the asteroid, which was because it's a very small object, you don't get gravitationally captured. You've got to basically brake and slow down to catch it. And then a bunch of observations at different angles to get different scientific results based on the lighting and position of the spacecraft. Along the way, we had some anomalies, some things that went wrong or that we didn't expect. And I'm going to go through some of those. Also of note, it was mentioned that I share two Guinness Book of World Records. The whole team earned them, especially the navigators. And that's for navigating around the smallest asteroid at the lowest orbit with an amazing 0.1 millimeter per second lowest thrust burn as a phasing burn to get the spacecraft lined up with the sampling site. An amazing feat of navigation. So when we were on our way out, getting ready for that braking burn, there was a forest fire, and we were worried that we wouldn't be able to speak with the spacecraft when it was going through this important asteroid approach maneuver when we had to do the critical braking to get ready to get near the asteroid. It was awfully close to the Canberra station, but it was okay. The spacecraft then entered and started doing its dance around the asteroid. It's, as I said, a very, very small object, so the spacecraft can turn on a dime. It can do all of these amazing maneuvers. In fact, the action of burning and turning helps you refine the position of the spacecraft. Government shutdown, and so I was sent home, and only the core team, the people on contract, were able to work. This was right before the spacecraft was about to go into its orbit. Another thing went wrong, which was that there was a nationwide internet outage. And so we lost the ability to send the commands to the spacecraft to actually go into that orbit. Fortunately, this was also over the Christmas break, and so there was, I believe, a Lockheed Martin engineer who was in Los Angeles and was able to take the commands directly to the Deep Space Network, I assume on a key drive, and then send the commands up that way because we couldn't send it directly from the operations center at Lockheed Martin in Denver. So we get into this low orbit. Fantastic. And there are rocks coming off our asteroid. Now, this was initially very, very concerning because you have these centimeter scale rocks, five-ish centimeters, that are being spat off the asteroid. Could they hit the spacecraft? Now, I wasn't worried because I was home furloughed watching C-SPAN. But other folks were like, well, actually, when you do the math, this is a very small object. These are moving really, really slowly, and space is big. So the chances of that actually hitting the spacecraft is low, and if it did hit, it wouldn't do a lot of damage because everything's moving so slowly. So it actually turned out to be a huge boon for science because you can do better gravity calculations on these objects which are going into orbit around the asteroid, falling back down, being lost, coming up and down. And that actually gave the gravity modelers more information on how to determine the inner structure of the asteroid. So, okay, we're in orbit, and then now what happens? Oh, back to work, thank God. We can find out what happened. And so we leave orbit to go and investigate the asteroid at different locations. And there's a big storm in Denver. This is our prime operations center. We had a backup operations center at Goddard, but this was a huge disruption because to shut down Denver, it has to be a big storm, and it was a big storm. Going back into our orbit, into our observation positions, it's an amazing dance that the spacecraft does to collect spectral and image data from all of these different angles. That's necessary because we're looking at a pile of rocks of different sizes. By the way, earlier on I said that the asteroid was made up of centimeter-sized pebbles. That was totally wrong. The data was accurate. Our interpretation was wrong. It's actually made up of enormous boulders. It was a huge, terrifying object with boulders bigger than like the launch tower. Very, very rough, scary place to go. So it turns out that our observation of why it was fairly smooth was based on our understanding of thermal inertia, which is as the asteroid rotates, the day side moves to night and the night side moves to day. As you can see how quickly the asteroid warms up and cools down. It was warming up and cooling down like poorly consolidated stones, not well connected. Well, these are big rocks that are also not well connected. So it is a complicated system where our assumptions failed us. So the asteroid did not meet our requirements. It doesn't work that way, so we have to adapt. And I don't know if you want to pass this around. You're welcome to. So yeah, that's a LiDAR shape model of the asteroid. You can actually download and print it yourself. That actually is a degraded resolution under current print technology. To get it at the full resolution, you have to print it out this big, and that's beyond my budget. So, but no, the asteroid is pitch black. It is extremely dark. It's an albedo of about 3% plus or minus, so like fresh asphalt. So that's one of the challenges of designing the instruments, to be able to look at something that dark, because there's not a whole lot of light that reflects off of it. Anyway, that was a nice digression. On to a moment that I think nearly killed our navigators. So when you have to operate in this object, you have to do all these maneuvers. And there's errors that build up over time as the position errors and where the spacecraft is. So we had this fairly unique situation. We had the scientists and engineers working together to get information on where is the actual spacecraft in its position by looking at the ground, looking at Bennu, observing the landmarks, the features on it. And normally we had, they had 24 hours to complete complete an update, to know where's the spacecraft, we're ready for our next maneuver, exactly where are we ready to go? Well, the Madrid Deep Space Network went out. We had to do a maneuver, and so they did a day's worth of work in 4 hours. I say day, I mean 24 hours worth of work in 4 hours. That was an amazing achievement. And one of the issues is that this is such a small object, we can't afford to not know where the spacecraft is. If the spacecraft has an error, it goes into safe mode, its instructions are burn towards the sun, get out of Bennu, because we don't want to accidentally hit the surface. Now, we learned that once we've done that, we go to stellar navigation instead of landmark navigation. Instead of looking at where we are on the surface of the asteroid, we look at where we are in space. It takes us a month to get back to know where we are in the asteroid. That's a huge amount of time. We only had 2 years at the asteroid funded. And also, just as there's a departure window to leave the Earth, there's a departure window to leave the asteroid. So if we missed that, we'd have to wait 6 years, and that's called being canceled. So they managed this, again, feat, went into another record-breaking low orbit, getting ready to rehearse getting our sampling, which was this death-defying maneuver because we initially had designed our sampling system on this smooth, featureless asteroid, which in fact was very, very, very rocky. And so we had to map the surface out of our potential sampling sites in great detail so that the spacecraft could navigate itself to the sampling sites to descend down, falling by the force of gravity, which is very small on the asteroid, to touch the surface. So we needed to have detailed images of the area to feed into the spacecraft computer so it would know where it was and would know whether it had to abort the descent. Well, the camera was focused by the LiDAR, and unfortunately, well after its lifespan, one of the lasers on our Canadian LiDAR failed, and we got a lot of pictures, had to repeat this maneuver. Oh, I also mentioned, while I'm talking about the LiDAR, is it was actually when I mentioned that we saw these particle ejection events coming off of Bennu, that was a surprise. And we detected it from doing, we wanted to do like a picture of the Earth, just for media stuff, just to see, here's the Earth in the background and Bennu up front, and one of our astronomers was looking at that and saw, what are these little things? Well, it turns out that the Canadian LiDAR had already detected them. Now, when they were doing their first testing, they shot the LiDAR at Bennu, and they shot it off in space. And they got returns from the LiDAR just shooting off in space. And we thought, oh, this Canadian piece of garbage, it doesn't work. Well, turns out that they discovered these particles before anyone else did. It worked beautifully. So going back and orbiting Bennu, then there was this little thing called the pandemic. And we had to both learn how to operate the spacecraft and how to operate each other remotely. And so one of our plans was to do rehearsals. So we'd fly the spacecraft to do everything except collect the sample, descend down for first match the location, and then back away, and then match the location, descend down, and then back away. These were all done to make sure that we minimize the risk, because touching an asteroid for the first time is really, really scary. Well, so we had to do this remotely, which was unfortunate, but we were all suffering. One of the other things that we discovered while we were at Bennu is we were able to fly along Bennu all this time and refine the impact probability of this object. It has a 1 in 1,700 chance of hitting the Earth, 32 approaches in the late 22nd century, so you've got time. And the asteroid will come close to the Earth in 2135. And so the data that we have now from Bennu, that we've been able to bring back on how to operate a Bennu, how to look at the sample, the specific geometry of Bennu, will give scientists, engineers, politicians, the public, in 2136, the ability to make a decision that if we actually have to divert Bennu, so it doesn't impact the Earth in the 2180s and 90s, that information. So it's a gift to the future. So then that's one thing I'm very, very proud of and pleased about. Now, nothing for us to worry about right now, but this data will hopefully not need to be used, but if it does, it'll be there. So I've mentioned a couple of asteroids. So these are close-up images. This is asteroid Itokawa. This is actually what we designed our spacecraft based on as a model of what an asteroid looked like. And see it has these smooth regions that Bennu doesn't have, but we didn't know that at the time. But this is the only asteroid we had to look at this close up. Here is the asteroid Ryugu, which is a lot of ways very similar to Bennu, about double the diameter. And of course, Bennu has some details on the origin and chemistry of the objects as well as the spacecraft, if you want to compare them. Bennu and Ryugu are actually quite similar. They have maybe a similar provenance coming from orbital dynamics. You can trace back where it may have come from in the asteroid belt when it broke up. So it's from the Eulalia or Polana families. So there's asteroids that broke up about 1 billion years ago or so, or a little bit less, and it led to these two asteroids. So these two asteroids might have been neighbors. They might have been from the same parent, or might be coincidence. We don't know. But there's a lot of similarities to them, but some fine details that are dissimilar that we'll talk about. So I mentioned that Bennu is rocky. The initial design was to use our LiDAR to know when to touch the asteroid. That had an air ellipse of 50 meters. These big rocks here, these are death. So we don't want to touch those. So we had to instead use our backup system, which used the cameras. I mentioned again how we had to image the tag sites, the touch sites. This was our prime, and we had a backup as well. And so they had to design the system to get within an 8-meter ellipse, this little thing in here, size of a few parking spaces. Even within that, there are red spots that are also death, because the spacecraft could come down and then touch a rock and then bounce off at an angle and slam into this mountain. We had the ability to, the spacecraft had enough fuel to do lots of tags attempts, no problem. We designed the system to have 3 separate bottles of gas, so we could use each one to deploy the gas, fire it, mix up the regolith, and get our sample. But we only had time to map out 2 sites. And as the spacecraft descended, it was doing this autonomously because the spacecraft was 18.5 one-way light minutes away from Earth. So by the time we got receipt of the command that the spacecraft had started its final approach to the surface of Bennu, it was already over. We just didn't know it yet. And so this was all autonomous. It all had to be programmed in, so the spacecraft knew it could descend down to the surface and knew that if it was on top of one of these rocks, it could back away. Backing away would destroy the site because it would fire its thrusters down there and mix up all the rocks. And so our landmarks are now gone, but at least we didn't destroy the spacecraft. Anyway, they got within 73 centimeters from the center of the ellipse. Oh my God, 73 centimeters. That's an amazing achievement on an 8-meter ellipse that was initially designed to have an error of 50 meters. So this is part of the Regolith Explorer. We now know how to have a spacecraft autonomously go and touch the surface of an asteroid at a precision location, so future asteroid miners could take this technology, these ideas, and move on in the future. We touched the surface and made a mess. So here is the point of contact. We fired the gas and made a new crater. So the spacecraft was descending at 10 centimeters per second to touch the surface of Bennu. We had 3 independent mechanisms to know when we touched the surface. One was, I mentioned the pogo stick. The spring would flex. The other one was we can measure the inertial movement of the spacecraft, know when it slowed down. The last one, we had a timer, so we knew when it started, and we knew when we should touch the surface. Well, it turns out that the science team got it wrong again. Sorry. That the surface was nearly cohesionless. We were only off by 6 orders of magnitude in our prediction. So the surface is much, much softer than we thought it would be. It's like a children's ball pit or maybe fresh fallen snow. And so the spacecraft was descending at 10 centimeters per second, touched the surface, kept going at 10 centimeters per second, didn't slow down. The spring didn't compress, no change in moment of inertia. The timer went off, fired the gas. That slowed the spacecraft to 5 centimeters a second, still going down. But then automatically, on a timer, the thrusters fired, the spacecraft backed away. So when the gas fired, it made a crater in the middle, and there are positions where the thrusters went down and made a plume. So here's a simulation of the spacecraft descending and actual images of the tag head touching. These are the lenticulars you have. You can see that the head moves down, it touches the surface, descends half a meter below the surface because the spacecraft was still descending. And this is actually an ideal situation to get lots and lots of sample. And it like I said, it made a mess. And the follow-on mission, if that is allowed to continue, called OSIRIS-Apex, is going to asteroid Apophis and doing what they call an air tag, where the spacecraft will descend near the surface of the asteroid, fires thrusters. There's no tag arm left, no gas left, but the fire the thrusters, make a mess there, and take new spectra to understand better asteroid Apophis, which does a close approach for the Earth in 2029. We had another problem, which was this is our collection head here. And you can barely see it, but right there, there's a little black shadow. And that is probably, if we do it elegantly and quickly enough, probably this rock, which is the largest stone we retrieved from Bennu. This is only a model, not the real one. I'd be shot if I pulled the real one out of its facility in Johnson Space Center under nitrogen gas, never touched by human hands. Something like this rock, the biggest one we have, got jammed in there and allowed material to escape. Our requirement was to get 60 grams of regolith. That's enough to do all the science we want and have plenty left over for the future. We believe that these rocks here being lost, as we were looking at the TAGSIM head to image it, was 60 grams floating off into space. I imagine that when we collected the sample, that the head went underneath the surface. Ideal conditions, we probably had 2 kilograms of rocks. But then as the spacecraft was backing away, it was probably like a crop duster plume of just dust falling out of it. And so that was lost, but we still got our sample. And this was designed to get the minimum amount of sample required. That's how you do engineering. And if we had designed it so, like, let's make sure that this can't get jammed open, why would it get jammed open? If there's rocks inside. If there are rocks inside, that means you already have your sample. So don't be greedy. Just get the sample you have. Anyway, the sample head was then put in the sample return canister, locked down. The neck was severed. Let's see if we can get that to go again. And this was actually done in real time. Commanding the spacecraft with 18.5 light minutes each way. You can see that they tug and to make sure that it's in. The sample return capsule closes down and locks in place. And it's time to go back to Earth. So this is the last time we see the sample return capsule from the spacecraft. Here it is being ejected, headed towards Earth. Here it is in Earth's atmosphere. This is September 24th, 2023. We had a little problem, but the parachute deployed perfectly. The second one deployed perfectly. The first one didn't deploy at all. But that was okay. We were extremely lucky. It landed exactly right. In an ideal location. It was wonderful. The main parachute was over-designed, so it had plenty of capacity. There was miscommunication. There's a saying that engineering is easy, communication is hard. The capsule was designed based on the Stardust capsule that went to Comet Vote 2. This was a build to print. The Stardust mission was under the Faster, Better, Cheaper program, which meant there wasn't really a print, because it was designed to be as quick as possible and as cheap as possible. And there was a print, but they discovered a mistake in the print where there's the main chute and the main mortar. the main motor fires the drogue chute, not the main chute. And so they connected the wires from main to main, and that was backwards. But as it is, it landed perfectly. We were extremely lucky. But as my colleague from the Smithsonian Natural History Museum said, that if the capsule had crashed, it would have been the best documented meteorite of all time. And so what we did was make sure that the capsule was safe. There's a battery inside that could have burst into flames. It didn't, thankfully. Document the area, that is, understand the potential contamination environment from the range. So this is at the Utah Assessment Training Range, about an hour and a half outside of Salt Lake City, and about an hour from the closest hotel, except for the one that's actually on base that only has space for about a quarter of the team. So that was fun. But anyway, document the area, make sure we collect samples just in case there's a breach or dirt got inside so the scientists could look at that and back it out. Wrap it up, and then fly it on long line to a temporary clean room where it was disassembled. The next day, flown to Johnson Space Center in Houston for disassembly. We had another little problem, which is that we had deliberately designed these fasteners not to use any lubricant because we don't want to contaminate the sample. And there was a non-zero chance that some of them could have seized, and 2 of them seized. We were actually able, the curators were able to remove 70 grams of material with tweezers and spoons from the inside of the sample, which actually met our requirements. But then they took a few months to develop a new tool because you can't just go in there and drill it out because that would, use a greased motor inside of this glove box that's under nitrogen with you're dressed head to toe in beautiful polyester, wearing nitrile gloves inside of other gloves. So it's a very difficult situation. You can't really bend your shoulders. You're working like this. You're like little T-Rexes. And so they had designed a tool that could apply enough torque to the screws, to the fasteners, without stripping them and setting up a shower of metal shards that would contaminate the sample. So they did that. They practiced. Wonderful job. Just took some time, but we had accepted the risk that we could lose some time instead of designing a new tool for every single possible fastener, because there were 100 fasteners and any one of them could have gotten stuck. And the fasteners, one of our mistakes was we should have made sure that all the fasteners were the same kind. They weren't. Oh well. So we lost some time. But in the end, we got double our requirements. We needed 60 grams. We got 121.6. Most of it right here, and what was scooped out, you can see the curators were scooping out gingerly and more aggressively, and then just scoop. There was a little bit on the surface, on the avionics deck outside of the sample collection device, and when they got the head open, they were able to pour out the rest of it. 121.6 grams, double the requirement. And this rock is this rock, just for context. And so what is the Bennu like? What is the Bennu sample like? It smells of sulfur, gunpowder, and burned marshmallows. It's really black. This doesn't do it justice on how black it is. It's like coal from a distance, with some glints as well, and some this weird white stuff. And when this rock got jammed inside, I said to myself, this rock had better be special to have thrown away a kilogram of the material. It turns out it really is special. It's one of these weird white ones, which is the most aqueously altered, the least primitive of the rocks that we see, with lots and lots of evaporites. So there are different textures that we see. There are these angular rocks like this, and what we call hummocky rocks that look like cauliflower. And when you look at Bennu, there are also these angular rocks. So this is the largest boulder in Bennu, called Ben. And there are also these hummocky, these cauliflower-shaped rocks. And so the morphology that's seen in the macro scale is also visible in the micro scale. Interesting. If you go to the Smithsonian Natural History Museum, there's a small exhibit on Bennu with a piece of Bennu you can see. This is an XCT scan of this rock. So this is like a CAT scan looking at the layers. And you can see it's very complicated. There are these vugs, these holes veins. It's a very complicated little rock that will take decades to understand. However, of the sample, our science team has analyzed about 14% of it. We were allowed to analyze 25%, but there's just so much to do. There's so little time. We've only done 14. That's probably all we'll have time to do. 55% of it has gone to 0.55 has gone to JAXA in exchange for Hayabusa 2 samples, as well as information about their encounter with their sample, with their asteroid, in exchange of personnel. I also mentioned contact pads. There are these things here, 24 little patches of stainless steel Velcro that touch the surface and grab little tiny grains. Samples, 4% is headed to Canada in exchange for the LiDAR that gave us that shape model that's so beautiful and also allowed us to understand the risks of the surface and a whole bunch of science. The rest of it is at NASA Johnson Space Center. And these are the QR codes for the collections that you can scan and you can see what they have and you can write a proposal to look at the sample yourself. So you, your students, your children, your grandchildren can come up with ideas that we don't have, technologies that don't exist now to answer questions we haven't thought of. A member of my group, Jamie Elsula, she was the PI of a program that studied Apollo 16 samples that were collected before she was born, using a technique that was not invented yet to answer questions that in this case were thought of but couldn't be answered until now. So this is the legacy of this mission, that we will be able to deflect perhaps Bennu if necessary after 2135, and we have this wealth of material that can be studied. It can be studied with scientific instruments all around the world, some which are the size of the launch pad. This is a cyclotron beam, and for scale here is an SUV. This whole building is really the instrument. As well as things which are too fussy or too difficult to fly and can be designed and updated and changed based on new information we find. And again, more for the future. So we have a sample analysis plan that we've been working on. This is the organic sample analysis plan in brief. We just want to make sure that every scrap of sample is analyzed to its fullest. And then we can cross-compare samples with other laboratories to make sure that we're looking at the same thing, we understand it. And so we have 12 hypotheses with 54 sub-hypotheses that we're testing and publishing on, but they can be broken down into 4 categories. What does the sample tell us about the history of the solar system? From this formation of the cloud all the way up to the formation of the crater that we got the sample from. How does the sample compare with what we saw from the spacecraft? How has the sample changed since it was collected? And does the sample contain organic compounds that could have influenced the original life? That's my passion. And so here's some data. We know from neon isotopes that the location that the sample was collected from is between 1 and 6 million years old, so very, very young, very fresh site. However, it also contains silicon carbide grains that predate the solar system, from a red giant star that was emitting particles that were then incorporated into the forming solar system. So the very old and the very young are all within the sample. We also discovered that this is the precursor asteroid out of which Bennu formed was a very, very wet place. Dr. Henry would have been proud to see that a hand sample from the Smithsonian Mineral Collection was actually used to notice that the texture of this piece of Bennu looks a lot like the same hand sample. So we detected trona in the sample, so that's a sodium carbonate, as well as sodium fluoride. These are materials which are deliquescent. They will suck in water from the air. These are very small crystals. They'll suck in water from the air and dissolve and melt. And so if we hadn't gotten the sample back from an asteroid, kept it under clean, dry nitrogen, these would have been lost. So you can't see these in a meteorite. This is why we need sample return, to understand that Bennu came from an asteroid that was extremely wet with alkaline fluids, pH 8-ish or so, that a very, very wet place that dried down to create these evaporites, these salts, and a clement, no more than room temperature environment. We also discovered lots of ammonia. And so here is the Bennu has a fair amount of ammonia. These are other meteorites that have been looked at with different methods. Here's Ryugu, extremely low ammonia. Now, if you're very clever, you'll say, wait a moment, I saw you fire your thrusters back away from the asteroid. What thruster did you use? Oh, we used monopropellant. Monopropellant, that's hydrazine. That disproportionates into nitrogen, hydrogen, and ammonia. Weren't you worried? I'm like, well, yeah. That's why we collected some of the fuel as the spacecraft was being fueled up at Kennedy Space Center, and analyzed the isotopic ratio of the nitrogen in that fuel, compared it to the ammonia from Bennu, and found that they're profoundly different. So we now know that because of this, this ammonia did not come from Earth. We can also look at rocks at very fine scales, and so this is a specific stone, well, very small stone. This is 250 microns, and you can see here is a solvent front. So there's fluid moving through this stone. On this side is high sulfur, on this side is lower sulfur. So this was not at equilibrium. This is a very complicated object with pulses of liquids that went through it, a lot of water, but it stopped part way. And there are probably multiple pulses. So it's a very complicated history. And you can start asking yourself, well, it has this ammonia, and the ammonia isotopic ratio tells us it came from an icy object, from the outer solar system past the orbit of Jupiter or maybe Saturn. We know that it was an undifferentiated object. I'll show that in a moment. Salty, cold, kind of like a comet, but comets don't have much rock-water interaction. We see lots and lots of clays. Well, it's maybe like an ocean world, like maybe Ceres or Enceladus. Very, very wet, lots of ammonia, extensive water-rock interactions, cold, salty, but these are differentiated. So they had a core that melted. Bennu never melted. What is it? So I can tell you what it isn't. It isn't contamination, with the exception of this area here, where there was some interaction during the plane flight, and due to some fine details, even under the most careful protection during the flight, there was a little bit of contamination in this 1 gram out here that is isolated from the rest of the sample. I'm working on a paper that describes that, but the bulk of the sample is pristine. We compared the sample to what we observed in space. So our spectrometers told us that we had phyllosilicates, iron sulfides, magnetite carbonate, hydrated xenoliths. Well, those are rocks from another asteroid that we saw, maybe from Vesta. Well, we've got phyllosilicates. That's that extensive rock-water interaction. Tons of iron sulfides, amazing amounts of magnetite, lots of carbonates. Is it hydrated? Oh, yeah. It's very, very wet. In fact, it has a huge amount of carbon and a huge amount of nitrogen. 0.25% nitrogen, that's a lot. Almost 5% carbon, that's a lot. No xenoliths detected yet, so those are rocks from like basalt from asteroid Vesta. We've only looked at a small part of the sample. And we also discovered phosphates. So these were unexpected and not detected by the spectrometers, because they're not really good at detecting phosphates. They're also not expected. And so there are these crystals, especially on this big weird rock, that are very phosphorus rich. And phosphorus is an important compound to the origin of life, or elements. We also were able to compare Bennu with its spectra with various meteorites and see how does it compare. And in fact, it's very similar to what's called a CI class meteorite. Don't worry about that. It just has a elemental distribution that's very similar to Ryugu, as well as to this kind of rare meteorite, which are this class here. I don't think I've got time to go into this in great detail, but there's a lot of different types of meteorites that have been studied. A lot of them have been studied for amino acids over the years. And based on the various different types of carbonaceous type meteorites, with these arcane names based on basically the nearest post office where the archetype was found. So you just got to memorize them. And so one example of it is the emergence meteorite that landed in Australia in 1969, which is a great example of one because there's a lot of it. This is one of the ones that was practiced on for the Apollo samples. And so, for example, there are likely over 1 million diverse compounds in it, so it's extremely chemically rich. 2% carbon, not quite as much as Bennu, and lots of compound distribution. So we can compare what we see in Bennu to what we see in meteorites, like Murchison or others. And so if we look at the isotopic space, so this is looking at the total deuterium in the bulk rock versus total nitrogen-15 in the bulk rock, you can plot out a bunch of different meteorites. You can see that they fall into categories. So CRs, we don't care what CR stands for, but these are over here. CMs, like Murchison, over here. CIs, remember I briefly mentioned that the elemental composition of Bennu is just like a CI meteorite, except in carbon nitrogen, where it's fairly different. So here's Bennu, here's CI. Ryugu is over here. So these are all quite distinct from each other, even though elementally they'll have the same distribution. And here are what's called C ungrouped meteorites, which are oddballs, and they're sort of Bennu-ish, but not exactly. We can also we can plot the amount of bulk carbon versus bulk nitrogen, and look at different compound classes. And so here's that Murchison meteorite. You can see that it's mostly carboxylic acids with some amines and some amino acids, not very much. Here's Ryugu, the sister asteroid of Bennu, and it is almost entirely carboxylic acids. Here's one of these CRs over here that's equally distributed. Here's Tarda, that's one of these weird ones over here that looks kind of like Ryugu. Orgay, a CI1 over here, like these. And that's kind of like Bennu, but not exactly. It's its own thing. We went to the right asteroid. This is like something we have not seen before. Really interesting. We have seen a bunch of amino acids, 14 of the 20 protein amino acids, as well as 19 others, and all the DNA and RNA nucleobases, as well as other nitrogen heterocycles, and a bunch of amines and carboxylic acids. So it's a rich mixture of organic compounds that are important for life. We did some analyses at Goddard, for example, and this is the way we do amino acid analyses, where we would take the sample and then do an extraction, pull out the liquid. This is part of that giant flow chart. This is one little step, and we can analyze it for amines and amino acids in two different ways. One gives us the chirality, one gives us the abundance in a different way. And we can compare them to a blank, always run a blank, a sample, and then Murchison. And you can see that it's its own thing. It doesn't have the same complexity as Murchison has. A lot more glycine. It's also racemic, which I'll talk about in a moment. And so we can look at all the amino acids in a meteorite. So here's Murchison again, and it has this rich array of compounds. 96 amino acids are named in the Murchison meteorite, and here are several of them. So these are all isomers of each other. This is the 5 carbon amino acids. There's a whole bunch of different isomers we can isolate, and we can use that to try and deduce something about the reaction mechanism that form these things that happen in the asteroid. So if we look at Murchison, we can look at the alpha position of the amine on the amino acid and see that this dominates. And so this makes us think of a Strecker reaction, the Stanley-Miller-like synthesis that would lead to these, as well as some betas, gammas, and deltas that have other reaction mechanisms, but dominated by Strecker, by this reaction. And we look at other meteorites, and as well as Bennu, and we can see that there's this is kind of diagnostic. So here's the dominated by Strecker reaction. Here's the CMs and CRs like Murchison. Here's the CI, like Orgay, and it has very little of the Strecker and a lot more of the gamma amino acids. Bennu is like none of them. And then there's other extreme cases. If it's extremely hot, we find out that you get almost all of the straight chain linear amino acids. So getting some clues about the mechanism, and they inform us a little bit about we can look at the petrology to see what the samples were like, and it seems to correlate well with what these amino acids tell us. So we have two different mechanisms to tell us something about the history of this rock. We can also look at the distribution of different amino acids, looking at the ratios of alanine, glycine, whatever, and we can see that, again, Bennu is very different. It has a lot more alanine to glycine than, say, Ryugu does, quite different, and quite different from Orgay, which is, again, has the same elemental distribution. Very different from Murchison, reminiscent of Winchcombe, a sister of Murchison, but not really. And these weird ungrouped ones are kind of similar. But again, remember, Bennu is not at equilibrium. And so the sample size we look at probably helps determine the ratios we're seeing, because if you get more of this side versus that side, you might get different ratios. It's a complicated rock. I mentioned briefly chirality. So chirality are is a physical property of compounds, sort of like Tetris pieces. They are non-superimposable mirror images, like your hands. You can have they have distinct chemical properties. So the difference between, say, D and L methamphetamine is the difference between dangerous illegal drugs and a mild decongestant. But on Earth, biology uses almost exclusively L amino acids and D sugars. And breaking chirality is a huge mystery in the origin of life. How did that happen? We can use laboratory techniques to isolate them and separate out the different enantiomers, which are chemically identical except that they are mirror images of each other. They're not like matter and antimatter; they don't explode if you touch them, but they are physically distinct. So you can do a reaction, form a different complex, and separate them out. So if you do an analysis, they might have different retention times. You can isolate the different compounds and say what the ratio of D versus L amino acids are by different techniques. And I'm not sure I want to go into this much, but there's a lot of different ways of being sure that you know what you're talking about. Looking at to make sure you have confidence in the detection of chiral excess. So I made up this this sort of Trivial Pursuit-like wheel of different tests you can do and understand how confident you are of a detection of a chiral asymmetry. And so one compound is very, very good at that, and that's isovaline. We have very high confidence that there's a real enantiomeric excess in some of these meteorites based on passing all of these tests. And Bennu is racemic. We had predicted, based on this trend, that the more aqueous alteration, the wetter the asteroid, the wetter the rock, the more excess of one chirality over the other one there is. You expect them to be racemic, so be the same, because it comes from an abiotic mechanism. But we found this excess in many samples over careful experiments. We had predicted that, well, Bennu is a very wet rock. Wet rocks from space have lots of L excess. Nope, we were wrong. So that's only 20 years of research. We'll find something else to do. Isovaline is not the only one. Here's isovaline that passes all these tests. These are all of the other compounds that have been detected in meteorites and proposed to have an enantiomeric excess. This is applying my little test on how each of these did. And some of them I don't think did a very good job of making proof. Others did an okay job. And of course, isovaline is the gold standard, which again is racemic, not following the predictions in Bennu. So this is why we do science, to be surprised. We can try and understand the reaction pathways that can lead to the formation of these amino acids and where maybe a chiral asymmetry could be introduced in the meteorites, but again, not in Bennu. And we can try and look at the precursor or degradation compounds and deduce the pathways. And these have been studied in a number of different meteorites. And we've detected like secbulamine, but there's no excess in Bennu or in meteorites, even ones that have an excess of isovaline. So this reaction pathway is not active. We can look at these other precursors and see which reaction pathways are active or not active. And this is an outstanding mystery in astrochemistry and the origin of life. How did isovaline and other related compounds from this list get their enantiomeric excess? Why did Bennu not have it? Some of them could be explained by contamination, but not all of them. This one's isovaline is really good. It passes a lot of these tests. But it's an outstanding mystery. I'll also mention that Bennu is a very complicated rock, as I've said, with over 16,000 different molecular formula. containing carbon, hydrogen, nitrogen, oxygen, sulfur, and magnesium. That's covalently bound magnesium, not the salt. And that Bennu is rich in nitrogen chemistry, unlike Ryugu and Murchison, which are rich in sulfur chemistry. It's a different beast. We went to the right asteroid. So we can start saying, putting this together, what does this tell us about the origin of life? We know that the primitive solar system was available on the early Earth or elsewhere. Meteorites came from a range of environments that reflected their organic chemistry. Bennu is not like a meteorite. That could be because it's just a coincidence of sampling. It's also, Bennu is very, very fragile, and so it probably wouldn't survive landing on the Earth. We know that Bennu is ejecting particles and across the Earth's orbit, so there ought to be a very small Bennu meteor shower in the southern hemisphere every September. It's been looked for, hasn't been found yet, but also ought to be very small. Bennu's parent body could qualify as a habitable world. It was cool, salty, mildly alkaline, very wet, lots of soluble carbon, nitrogen, phosphorus, and sulfur, all the organic compounds for life. Why didn't life form on Bennu? What did Earth or Mars, Enceladus, Europa, Ceres have that Bennu didn't have? Bennu is now an excellent case of what was special about the Earth? What went wrong on Bennu for life not to happen there? It's a great example of challenging some of our hypotheses about what we thought was necessary for life to happen. The chemistry required an alkaline, salty, moderately temperature environment, rich in organic compounds. It sounds like Bennu. Well, didn't work. And so these are ways you can start connecting the dots to understand looking for life in the solar system. You want to look for biosignatures. That is the search for life. These overlap with prebiotic chemistry, the abiotic synthesis of the same compounds that are found in life, the same chemistry. You can look at meteorites that have the same prebiotic chemistry and also suffer from contamination when biology touches them. You can look at a primitive body like Bennu to understand the sort of chemistry that comes from meteorites and the prebiotic chemistry without being contaminated. You can send missions to places to look in situ. Send a rover to look at an object, and that tells you something about prebiotic chemistry and very little bit about biosignatures because of the nature of flight instruments and the complexity of looking at biosignatures. But you need all of these together. You need to get the geologic context, the knowledge of the endogenous chemistry and the exogenous chemistry to look for non-terrestrial life on an evolved body like Mars, Enceladus, Europa, Ceres, what have you. And so I'll close by saying that during build-in tests, we lost our PI. We almost lost an instrument due to politics and money. The launch complex exploded. There was a blizzard, a train wreck. There's some QC issues that happens. I mentioned the forest fire. Internet outage, DSN, bomb cyclone, we missed a crucial DSN pass, and there was a global pandemic. With all of that, the mission was on time and under budget. There was only a single safe mode during outbound cruise that had no actual impact. It was just human error that had nothing really to do. We lost one of the lasers on Ola well after its expected lifespan. The other laser managed to work fine. The sun didn't give us good solar flares for the student experiments. Pity. They did detect a black hole, but that's not really our mission. But they did that. That's nice. The drogue chute deployed late, and 2 TAGSIM fasteners were stuck for a while. So through all this, it's been a remarkable team and an honor and pleasure to work with them over these 20 years. And I'll finally thank you for your attention and invite you to learn more about the mission and visit the sample catalog with this QR code and come up with your own science and your own questions for you, your students, or your children. Thank you.
Are these people great or what? Really? I mean, it's amazing what they do. Anyway, we do have time for some questions, not as much as usual. Blue microphone.
Ciprian Ivanov, member. Did you say that you detected methane? And what other significantly volatile hydrocarbons did you find?
I did not say we detected methane. We have an experiment that is in preparation that will look for the volatile compounds. Actually, we have two of them. One's at Goddard, one's at Brown University, doing two different techniques to look at volatiles extracted from the solid sample. Those haven't been done yet, and of course haven't been published yet. We also had a trap to look at volatile organics that are coming off of the glove box, and that collected information, which is complicated being analyzed. That'll be published at some point. But I've not discussed the hypervolatiles. But ammonia, methylamine, ethylamine, propylamine, butylamine, stuff like that. More to come.
Brad, microphone.
I'm Bob Hershey. I'm a member. You were providing for any changes in samples since you collected them. Did you see any?
So the change in the sample, I mentioned the lack of contamination, except for around the edge. We also saw there's like this rock, which just went away. I didn't bring the other one, but you can puzzle piece rocks together. And so you can't see it here, but this rock right here has a little piece that actually fits perfectly in it. And so some of the rocks broke up. We don't yet know if that, or we may never know, if this piece of rock broke up during collection or during sample return when it came down and landed in Utah. So these are the sorts of things that we've seen of changes. Measuring the volatiles over time, that's ongoing work. More to come.
We have one from the chat on the YouTube feed.
Our first question comes from Jin Talons, who is a member. Why did the mission emphasize regolith over subsurface samples, and what additional information could these samples provide?
Cost. So we need to design a mission that has low risk and controlled cost. Drilling into essentially gravity-free objects. The surface gravity of Bennu at the equator is about 8 micro-Gs. For comparison, the International Space Station experiences 3 micro-Gs. And so having the spacecraft not bounce off the surface is very, very hard. We actually designed it to bounce off and come back after doing a collection for 5 seconds. So to go down and drill in, get a drill core, and bring it out would be wonderful. But then you've got to keep it intact and put it inside of the capsule, bring it back to Earth. All of a sudden, you're not in the New Frontiers budget anymore, your flagship, and otherwise known as not being selected.
Thank you.
Next question from the web.
Our next question is from Kirby Runyon, who is a member. What mechanism is responsible for lofting rocks off the surface of Bennu? Did the rocks escape or fall back?
So they both escaped and fell back, and sometimes when they fell back, they made another plume of rocks as they hit. There were 2 main hypotheses about the cause of the rocks. One was that you have micrometeorite impacts that hit the surface and cause a splay of rocks to come off. And because rocks come up and come down and hit again, that happens. That's evidence for it. But there's also thermal cracking. The asteroid goes through thermal changes as it goes from day to night. The surface of the asteroid at the equator is up to 100 C because it's a very, very black rock at around 1 AU. And there are, we have good evidence of trapped gases. We haven't finished characterizing them. And so these could explode as they get warm and pop out. And so as we are learning more and more about the trapped gases and vesicles inside of it, we might have a better mechanism for, was this dominating? Was it thermal stresses as the temperature changed? Was it explosion of trapped gases as the temperature changed? Or was it micrometeorite impacts on Bennu? Very good questions.
This is Brooke Lakeview, non-member. I have a quick question for you. Are there conditions where inorganic compounds can evolve into amino acids? Is there like a thermal or other conditions where non-organic molecules can evolve into organic ones?
So part of it depends on how you define organic. So if you take hydrogen cyanide, which I would say organic, some people might argue with me, and you react that with ammonia, you can make amino acids. You could synthesize the cyanide from, say, taking nitrogen gas and maybe graphite and expose that. You could get it with effort, but it's much easier to start with something like formaldehyde, cyanide, methylamine, something of that sort. And of course, it has to have carbon, unless you're doing nuclear fission. You've got to start with the right compounds and the right elements. So it is technically possible, but not easy. I wouldn't bet on it.
So what did Miller do?
I guess you could take, if you believe CO2 is inorganic, you could start with that. That would work.
Okay, red microphone.
My name is Al Ehrlich. I am a member. You raised the issue of chirality. I missed it perhaps, but did you say that you've now seen chirality in both chiralities? Because I was under the impression that everything on Earth was of a single chirality.
So on Earth in amino acid space, biology is almost exclusively left. There's some right. Special cases. There are some fungal peptides, for example, that have the other chirality because bacteria really hates it, and so it's a poison, vice versa. So there's a constant war going on in the microscopic realm, and using these chiral tricks are helpful. But that's off the topic. So we detected both chiralities, equal amounts, which is what you'd predict if you were going to synthesize something from abiotic means. And that's what would have been 30 years ago. We'd have said, of course, there's going to be racemic because that's what you make. But there's this history of the last 25 years, 30 years, seeing that there's this excess of left-handed isovaline and a few other amino acids by up to 20% in certain types of meteorites that we would have predicted Bennu would be like. There's also is an excess of right-handed sugar acids and sugar alcohols in a couple meteorites. We don't have that detection yet on Bennu, and there's not been a detection on sugars themselves. But it is either exciting or frustrating that the same chirality excesses we see in meteorites are the ones we see in biology. That either means that there's all contamination, we're wasting our time. We've got good isotopic evidence that says probably not in all cases. It means that when you look for life elsewhere, if there's some force that primed the solar system for left-handed amino acids and right-handed sugars, that if you detect left-handed amino acids and right-handed sugars on Mars, maybe it's from meteorites, maybe it's from biology, maybe it's from Earth. That makes the science more difficult. But it's one of the great outstanding questions. But yes, racemic.
Thank you very much.
Blue microphone, and just pause for a second. Now,
Hi, Matt Kaywood, member. First, who got to smell the sample? And second, what did we know about Bennu's parent in terms of size, age, composition before this mission, and what that's different do we know now?
So the curators working on the sample smelled the tools that they removed from the nitrogen-filled glove box, and that's where the odor came from. They didn't actually smell the samples themselves because they never leave the nitrogen purged glove box because we don't want them to interact with air because air has moisture and would oxidize it and ruin it. Let's see. We have evidence that Bennu came from a large parent asteroid, 100 kilometers across sort of scale, past the orbit of Jupiter, Saturn, contained ammonia-rich ices that melted, and through many pulses of different phases of melting, had liquids that went and percolated through the rocks and evaporated away. That mixture that then lost most of its water, drifted to the inner solar system in the asteroid belt, where it broke up about 1 billion-ish years ago, and leading to Bennu, which was a piece of that broke up and reformed into this rubble pile. Bennu is a spinning top shape because it's like a dust bunny. It's loose regolith. It has interior voids. It's barely held together, and that drifted in the inner solar system in near Earth space. But there's More coming as we have more isotopic evidence that looks at different phases. We have more. There's a paper that's been, I think, accepted but close, talking about some of the surface properties in recent times on Bennu from those contact pads, the stainless steel Velcro. You can look at. There's a lot more to come because working in the glove box with like a T-Rex is so difficult. Getting the samples out took longer than we had hoped, and so for the future, we want to do the best job we can, not ruin the samples with impatience. So it's better in the long run. But that means we have to be patient, and science will come. It's just taking longer than I would have liked.
We'll take one or two questions from the web, and I think then we'll wrap up the Q&A.
We have a question from Shravan Rao from Melbourne, Australia, who is not a member. Will the designs and instruments for OSIRIS-Rex be used for future asteroid missions that more NASA research labs could propose and lead?
So all the missions have a heritage. So for example, the OSIRIS instrument, the one that was lost in the fire, that one had it derived from partly from the Ralph instrument, went to Pluto, and its successor is on its way to the Trojan asteroids on the Lucy mission. It's also similar things are used on some Landsat instruments. The thermal infrared instrument from Arizona State that actually derives from some of the Mars rover instruments, and as well as the Mars orbiter instruments. Some of the same technology there, and is used on follow-on other missions. The camera system that has heritage similar to the Cassini-Huygens lander. So all of these instruments have pieces and elements that are used in the past and will be proposed for missions in the future.
And our last question from the web, Eric from Sweden, who is not a member, asks, do you hope to find the other 6 amino acids for life in your samples?
We're looking.
Thank you.
You know, going back to the question before this one, it's really worth noting that besides the actual instrumentation, the institutional knowledge of people who've worked on a succession of missions like this over a period of decades in their entire career have a very, very rich contribution to every successive mission, and you just can't replace that. It's a treasure that the S has developed over the years, and that these people have devoted their lives to developing. So I thank them all.
Thank you.
And thank you, Jason, for sharing your time and explaining what you've been doing and what the results are. We have a very small token of thank you that we're giving you, which is a framed copy of the announcement of your talk signed by all the members of the General Committee on behalf of all of the members. A PSW rosette emblazoned on its side with the stripes emblematic of the symbol for the Henry, named for our founder, Joseph Henry. It's the symbol of induction, and the unit of induction is also named the Henry. And a copy of PSW Science Bulletin, Volume 17, First Edition, which contains many of the seminal papers and several histories and a list of the Joseph Henry speakers, Nobel Prize winners who've been speakers, and the like. And it's a good read for anyone who's even casually interested in PSW. So thank you very much. The
Thank you.
actual items are in the back of the room.
That's good. Thank you.
Before you go, the next meeting is a members-only meeting. It is the annual PSW meeting where we talk about the state of the organization and some of our plans. We're also going to have a topic for discussion amongst people. We're not sure what it is. Last year it was AI. Maybe that was premature given what's happened in the year, but we will have some fun with that. The schedule is being put together. It's up on the website. There'll be more information in due course. Hopefully we'll have, for once, the entire fall schedule up with all the information before it starts. So the first speaker of the fall will be Will Marshall, and he is the founder and CEO of Planet Labs. So Planet Labs has a constellation of small sats that picture the Earth twice a day, every day, the entire landmass. And this may seem pedestrian, but actually it's the first time that we've been able to get that kind of data for the entire Earth on a regular basis, to be able to see daily changes in everything from forests to what's going on in Ukraine and other countries. So that should be a very fascinating lecture. I should say that the resolution of these Dove satellites was designed to be able to see individual trees in the forest. I don't know if they quite got to that level, but they were very interested in deforestation and being able to track deforestation on a regular basis from space. Then we have Peter Shaw, who is very famous in quantum computation circles, and that should be fascinating. He was the person who first showed that a quantum computer on certain problems could outperform any classical computer, starting the serious effort to build a quantum computer. Adam Rees, Nobel Prize winner in physics, will be coming to talk. I think part of his talk is going to be about how he got something wrong. So it should be interesting. He'll probably address the Hubble tension, which is this problem that the measurements of the Hubble don't always agree with each other. And this has implications for whether the universe is accelerating and how fast it's accelerating. It bears on issues of how much dark matter there is, how much dark energy there is. So that should be a fascinating talk. I am not going to go through the other ones. I recommend you go to the website periodically to get updates. The other two people are going to talk about AI, various aspects of AI, and they should be fun and interesting. So with that, let's thank our helpers who ran cameras and all of that stuff. And I will accept a motion to adjourn the meeting to the social hour. A second. All members in favor? Anyone opposed? Too bad. Meeting is adjourned.